Good afternoon, and thank you for joining us for Ryerson's Metal 102. My name is Stephen Taggart, and it is my pleasure to be your host on this immersive and interactive journey into the world of fabrication. For the next hour, we will dive headfirst into all aspects of fabrication, from sheet to plate to long products. Our subject matter experts will lay out the key factors that go into identifying the most efficient supply chains. As you can see from the map on your screen, we have created a university experience. Our curriculum is based on the collective knowledge and expertise of Ryerson over the past 180 years. I will be your guide and make sure you get to each class on time. Let's take a look at our class schedule for today. We will spend roughly 10 minutes at each classroom: intro to fabrication and elements of a print, long products, plate products, sheet metal products, and quality. Matt Printmaster Stelzer will lead intro to fabrication and elements of a print. Zach, the long game Hicks, will educate us on long products fabrication decision-making. Ray, plate expectations Fleming, will teach plate products fabrication options. Jarrett, sheet music Jones, will talk all things sheet metal fabrication. And Tim, quality and driver, will give an overview of Ryerson's quality commitment. You'll have an opportunity to ask questions at the conclusion of each class. Do so by using the Q&A button at the bottom of your screen. We will try our best to answer them live, and if our team does not get to them, we will follow up after today's presentation. And yes, the Metal 102 video will be available starting tomorrow on Ryerson's YouTube channel. So, without further ado, class is starting. We don't want to be late. Professor Stelzer is ready to lead intro to fabrication and the elements of a print. He is very strict when it comes to being on time, just like Ryerson and their on-time delivery. They're all yours, Professor Stelzer.
All right. Thank you for the introduction, Stephen. My name is Matt Stelzer, and I am the Inside Sales Manager for the Ryerson Advanced Processing Division that covers Ohio, Michigan, Indiana, Kentucky, and Western Pennsylvania. Welcome to Metal 102. In my class, we will cover some industry terms and definitions that will repeat throughout the course. I will list some of the more common types of processing when it comes to sheet, plate, and long product fabrication. You'll learn about CAD file types and how each file type is specific to the part and how it's interpreted in the manufacturing process. I'll wrap up my time with you today by reading through a title block and identifying its features. We have a lot to uncover, so let's get started. We will begin class with a few definitions and terms. The first term is fabrication. Simply put, metal fabrication is defined as creating products or structures by cutting, bending, and/or assembling metal material. It's largely considered a value-added process as it consists of putting together actual products or structures from raw material. What is a blueprint? Blueprints have many names and are also known as drawings, manufacturing prints, engineering drawings, or simply just prints. Most prints are white and have black lines, but they are still often called blueprints. Think of blueprints as manufacturing instructions. They originate in the engineering department and give the manufacturing department all the information that's needed to make a product. Blueprints transform ideas into products and communicate information between engineering and manufacturing. The three basic elements of a manufacturing print are the drawing, dimensions, and notes. Prints contain all the information that is needed to make a finished product. A finished product may be anything from a simple part to a complex assembly. Quantities of parts to be made may range from 1 to millions. Manufacturing organizations that use blueprints range in size from small machine shops to large industrial corporations. In all cases, prints provide the information to manufacture a product. Most manufacturing prints have a title block, and within the title block are the manufacturing tolerances for that part. The tolerances are critical for how the parts fit together with other parts. Tolerances are communicated in fractions and decimals and can be in metric or in inches. The part tolerance can also help determine what process is chosen to manufacture the part. Part tolerances can be matched to the machine process tolerances that are best suited for producing the part on the drawing. Another industry term is kerf, or the material that is lost as part of processing or through the cutting method. Different cutting machines like laser cutting, plasma cutting, or oxy-fuel cutting remove different amounts of material due to the type of gas or electricity used to make the cut. Machinability is how hard or how easy it is to remove material through a machining process. Whether it's carbon or alloy or stainless or aluminum, each type machines differently. There are many factors that go into a part's machinability. Our sales engineers at Ryerson are well equipped to handle a variety of material types and processes. The last term on the slide is nesting. We want to be able to fit as many parts onto a stock plater sheet as possible to improve yield and maximize material usage. Part nesting can be achieved using computer-aided design software that allow the user to import files and manipulate them on a 2D plane. Now that we know that the manufacturing print is a guide that tells us how to make the part, the next step is to identify what process or processes should be used and how many of them are needed to get a finished part, while still satisfying the criteria outlined on the print. The more complex the part, the more processes will be required. There are many different processing methods. Some common types of processing you may be familiar with are laser, plasma, or oxy cutting. All three of these are considered thermal cutting because they use heat to cut through the material. Laser cutting could be either flat laser or tube laser cutting. Lasers use either oxygen or nitrogen to cut through the material and are ideal for a wide variety of ferrous and non-ferrous materials. Today's laser cutting machines can cut up to 1-inch thick carbon and stainless with ease. Plasma cutting uses electrically charged gas to cut through the material. Plasma cutting is generally used for parts up to 2-inch thick and used to cut stainless, carbon, and alloy steels. Oxy-fuel cutting, another thermal cutting process similar to plasma, but without ionized gas. Oxy-fuel cutting uses 99.5% pure oxygen to create a flame capable of melting through the steel. Oxy-fuel machines can cut up to 22-inch thick plate. There are cutting methods that do not use heat to cut through the material, like water jet cutting and machining. Water jets use a high-pressure stream of water with sand or another abrasive material to cut through a variety of metals and plastics. Machining is a manufacturing process that uses various types of cutting tools to remove small amounts of material from the workpiece to ultimately produce a high-precision part or component. Milling machines tend to be used for drilling or cutting shapes into a hard, solid material. Rotary tools on the milling machine can shave and slice a material in varying directions, depths, and angles and range from 3 to 6 axis structure. Lathes are not too dissimilar to milling machines, that they are both shape the desired material using spinning contact between the machine's component and the object. However, while a milling machine tool spins and or moves to work on the still material, the lathe rapidly rotates the material while introducing the tool to shave and shape the spinning object. Because of this method, lathes are best used for conical, cylindrical, or spherical shapes. At this point in the class, we know what a print is. We've covered some terms and definitions that will help us throughout the course, and we've covered some common processing methods. So now let's talk about two file types that are often associated with blueprints or manufacturing prints. Talking about CAD files. A CAD file is a digital file format used by computer-aided design software to create 2-dimensional or 3-dimensional designs, drawings, and models. It contains information such as geometry, dimensions, materials, and other specifications necessary for creating a physical product or structure. CAD files can be saved in various formats and can be easily modified, shared, and printed. They're widely used in industries such as engineering, architecture, manufacturing, and construction. The main difference between 2D and 3D CAD is the level of detail and realism in the design. 2D CAD is used for creating 2-dimensional drawings that represent the physical dimensions of a product or structure in a flat top-down view. In the manufacturing industry, think of burnouts or parts that are cut in the flat. 2D CAD designs are simpler, easier to create, and require less computing power than 3D CAD designs. Examples of 2D CAD are DXF or DWG files. 3D CAD, on the other hand, create 3-dimensional models that represent the physical shape and appearance of a product or structure in a more realistic way. It allows for more detailed and accurate designs including the ability to view and design from multiple angles and even simulate how it will behave in the real world. 3D CAD designs are more complex, require more computing power, and are often used in industries such as product design, architecture, and manufacturing. 3D CAD is great for parts that are not flat or have features that cannot be easily seen in a typical view. Examples of 3D CAD are IGES, STEP, or SolidWorks files. So you may be asking, how are CAD files different than shop drawings or to the manufacturing print? The drawing is used to validate the data in the CAD files. While the information contained on both are similar, the shop drawing typically includes more detail than just the electronic CAD file. Drawings have a title block. Title blocks contain information such as project name, drawing title, date, revision number, tolerances, part numbers. They also have general notes, plan views, elevation views, section details, and are very specific areas of how the item is drawn and may include additional information about the material and its construction methods. When possible, send both the drawing and the CAD files to ensure the part is made to the print. Now let's take a closer look at the title block. The title block is usually found in the lower right quadrant of the drawing. It contains critical information and acts like a roadmap to making the part. On the screen, you'll see a typical title block found on most manufacturing prints or shop drawings. Some of the critical information in the title block includes the unit of measure. In this case, the part is dimensioned in millimeters. The tolerance block. This gives us the allowable deviation from the specified dimension of the part. If the dimension on the cut piece is too far above or too far under the allowable deviation, then the part's no good and cannot be shipped to the customer. Part tolerances can also be a guide in selecting the most suitable processing method. Other areas of the title block are the material and the finish. In this case, the part is plain carbon steel with no finish requirement. Description, drawing name and number, and revision. Very important to include revision as parts go through engineering changes. The part number is used to identify the part and is typically referenced on all manufacturing and shipping documentation all the way through to the invoice. Well, that sums up the element of a print. What I hope you take away from this is that there are many different fabrication processes. You don't need to know all of them. Let Ryerson's advanced processing team select the right process for your part. Also, remember that the drawing file provides us with the instructions on how to manufacture the part. The CAD files provide accuracy and speed and contain lots of information, but lack some critical details only found on the manufacturing drawing or print. The print validates the CAD files. They work together. The title block contains a ton of information, but is also part of the instructions necessary to make sure the part is made correctly. And that concludes the introduction to fabrication. Thank you for your time. Back to you, Stephen.
That was a great class. I learned something new every time I listen to Professor Stelzer. The floor is open to the class for any questions. Use the chat button at the bottom of your screen. Okay, Ryerson team, here we go. Can you explain the difference between third angle projection and first angle projection? I see that referenced on drawings differing based on where the part was designed.
Best answer I can give for this basic introduction class is it's just another perspective in how you view the part. Some prints will give you top-down view, side view, multiple angles that you can see the part and see different features of the part.
Thank you, Matt. Okay. We are now going to follow 3 parts representing 3 different categories from print to finished product. Let's head over to the Long Products campus to kick it off. Talking about long, did you know Ryerson has been in business since 1842? Now that is a long time. Good afternoon, Professor Hicks. Take it away.
Thank you, Stephen, for the introduction. Good afternoon, everybody. My name is Zach Hicks, and I'm a solutions advisor on the fabrication team here in Minneapolis. Today, I wanted to discuss long products processing. You can see here, this is a print of the part we'll be using for this exercise. It is a 2-inch square carbon tube with a 3/16 wall. The customer orders this part in either 120 or 240 piece quantities, so there is some volume there. There are many options for processing tube. Today, we're going to discuss the 3 most popular and prevalent in the industry. First option would be machining. For those of you not familiar with machining, these machines can make precise cuts with high accuracy and repeatability. The features and tolerances on this part do lend itself well to being processed on a lathe with live tooling. However, one potential bottleneck would be that the operator needs to manually load and unload each part. Second option would be a tube laser. Tube lasers can cut tubing, channel, or structural shapes to length while adding holes or complex cutout designs at the same time. Tube lasers can also make precise cuts with high accuracy and repeatability, as well as utilizing an auto feed option. The auto feed option is handy for raw stock for any inefficiencies that may come from the operator having to manually load or unload each part. Also makes it ideal for high volume runs. Third option would be to hand process these. This would utilize traditional machines such as a Bridgeport, drill press, bandsaw to achieve the finished part. For a one-off part, that may work, but it would not be efficient for a run with any sort of quantity to it. This process also would require multiple fixturing, has multiple tool changes, and is a very labor-intensive process. So with that, our ultimate selection will be the tube laser for 4 reasons: efficiency, repeatability, speed, and cost. Let's take a look at these machines in action. Thank you. A couple key takeaways I wanted to touch on here towards the end of this. A major benefit of tube laser processing is really the reduction of secondary operations. Cutting a tube with a physical blade or a tool often leaves metal shavings and imperfections in the cut edge. These issues would require additional cleaning, deburring, and shaping processes to prepare the tube for whatever the end use would be intended for. Another benefit would be that no mechanical force has to be applied to the cut. Normally, a CNC punch or other machine would break through the material with a physical force, applying stress to the surrounding material and weakening it slightly. Using a tube laser to cut helps to ensure that the tubes are stronger at the point of the cut than they would be if a physical cutting tool was used. Lastly, and most importantly, is the diversity of cutting processes. CNC machinery enables a high degree of control and precision for many tasks, and CNC-controlled laser cutting is no exception. Instead of simply making vertical cuts, tube laser cutting machines can be used to make angle cuts, slots, etchings, bevel cuts, copings, and more. Thank you for your time today. Let's send it back to our host.
Thank you, Professor Hicks. I will never look at a tube the same way again. Ryerson has over 20 tube lasers strategically positioned throughout the United States. Question and answer time, find that chat button and fire away. Okay, Ryerson team, what is a red metal? Zach?
Oh, I'm sorry. I thought that I was waiting for a tube laser question. I apologize. Oh, a red metal is just another form of a carbon metal that we would provide to also be considered a copper, an aluminum, bronze, or anything in that category.
Thank you. Can a tube laser cut more than just tube?
Absolutely. We process many different shapes, structural forms, and I-beams in addition to square, rectangular, and round tubes on our tube lasers.
What is the largest diameter you can cut on your tube lasers?
We are currently installing a LT14 jumbo tube laser in our Norcross facility that will be able to cut up to anything with a 14-inch diameter or diagonal. It's a major capital investment that is going to give us that much more competitiveness and diversity in our cutting options.
What application would you recommend a tube laser for?
A lot of automotive rack companies use them. We do a lot of agricultural, poultry processing, anything that has a large volume run with a lot of angles. The great thing about tube laser cutting and the way that we cut and process the tube is it prevents or takes away a lot of weld preparation. These parts can be delivered to a customer, immediately be fixtured up, and immediately go to welding. There's no grinding or other prep work that would be required.
Okay. Another question from the group. How can you estimate the machine hours that our product would need?
We have an excellent group of programmers and utilize a lot of advanced software. We load in a CAD or a step file, run a simulation, make sure that there are no possible red flags that would pop up in terms of features that we wouldn't be able to cut due to a wall thickness, a location on the tube, and utilize just our group knowledge of being fabrication experts to make sure that we have an accurate time and that the product is going to be to the print and get the customer what they want.
One more, what are your typical minimum order sizes for parts ran on tube laser?
We'll make one part, we'll make 1 million for you.
It is. See, there's more questions coming in. I like it, active group. Are there issues with stress release in cutting away material?
No, not when it comes to tube laser processing. Because of the laser, it really doesn't give it too much of a heat affected area. So you would save some of that possible stress that would come from plasma and or oxy cutting.
Does the laser affect the heat treat properties of the metal?
It does not.
Finally, does Ryerson accept CAD files and cuts tube to the CAD drawing?
Absolutely.
I was under the impression that you guys only sell the raw material.
No, we'll do it all for you. We'll sell you the raw material, we'll cut it for you, we'll send it to you, we'll do whatever we need to do to make sure that you get the product you want at the price that you like.
Thank you very much, Zach. You are off the hot seat.
Thank you.
Time to take our journey into the world of plate products. Did you know that Ryerson can process plate up to 20 inches thick? Professor Fleming, you're at the plate. See what I did there?
Yeah, that's awesome. Thank you, Steve. My name is Ray Fleming. I serve as Senior Technical Sales within the Ryerson Advanced Processing team. Thanks for joining us today for a journey through a few different options we offer in thermal cutting of plate products. The first option we're going to look at today is laser cutting. Did you know that laser is an acronym, which means light amplification by stimulated emission of radiation? Whew, that's pretty complex. To put it simply, lasers work with a highly concentrated beam of light. We specialize in cutting all grades of carbon, stainless, and aluminum steel. The thickness range for laser cutting can easily run through all common gauge thicknesses in sheet product up to 1 inch thick in carbon steel. Advantages with laser cutting begin with a high precision cut quality. We can easily hold profile tolerance of plus or minus 1 millimeter or 40 thousandths, and hold tolerance as tight as 5 thousandths of an inch. Lasers offer a very smooth, clean, perpendicular cut edge, eliminating the need for most post-cleaning operations. Lasers are perfect for 2D profile cutting, which is just means shapes. Complex profiles, and we can accommodate almost any hole size, including irregular shaped cutouts, hex holes, slots, small diameter holes that can even run smaller than the material thickness. For example, we can cut 3/8 inch diameter holes in 1/2 inch thick material. And this cannot be done with traditional plasma or oxy cutting. Next, we're going to take a look at plasma cutting. Plasma cutting is a highly charged electric arc over 20,000 degrees Celsius. This offers the highest speeds available in traditional plate processing. Typically, we begin plasma cutting at 3/16 of an inch thickness and can go up to 2 inches or 50 millimeter in carbon steel and up to 4.5 inches thick in stainless steel. Our high definition plasmas can easily hold profiles of plus or minus a 1/16 or 3 millimeter. The speed and accuracy of a plasma makes it the lowest cost option. Profiles with radius corners are a perfect match for this process. With the increased speed of a plasma, some profiles with tight 90-degree corners and small diameter holes might be better suited for laser cutting. Another huge advantage is our ability to add beveling capability right on the plasma table. We can bevel up to 45 degrees, eliminating the need for secondary handling. And we can also include milling and drilling and tapping, saving post-operation steps in machining. Our last process we're going to look at is oxy-acetylene cutting. This traditional type of plate processing has been around for multiple decades. Just like it sounds, this method uses pure oxygen with an assist gas up to 1800 degrees Fahrenheit. Another great feature with oxy cutting is having multiple torch capability, running from one single torch to 12 cutting torches at the same time. And as Matt mentioned earlier, oxy allows us to cut over 20 inches thick in carbon steel grades. Certain grades and heavier plate thicknesses require a preheat pass to bring that material up to temperature prior to piercing and cutting the profile. This type of cutting takes true craftsmanship, and our machine operators are the best in the business. Slower than plasma cutting, but able to hold tight corners and profiles with less bevel effect on cut edges since they run at a slower speed rate. I've seen the cut edges on our factory floor and they would astonish you. The level of our cut quality is truly a testament to our seasoned professionals. The straightness and perpendicularity of the cut edges are unmatched in the industry. Now let's take a look at these methods in action. Thank you. I love seeing those sparks fly. Laser cutting, let's take a look at just a couple things. Highly tolerance profiles, including holes and intricate cutouts. Ideal for slot and tab configuration that can reduce the setup times for welding and even eliminate the cost for expensive weld fixtures. Plasma cutting, very fast, efficient method of cutting at a very competitive cost due to its speed and accuracy. And oxy cutting, our last process that we looked at, is truly a craftsmanship. Just like a finished carpenter, our operators have the tenure and experience that can be easily seen in the finished part quality of our product. Back to you, Steve.
Wow, very informative, Professor Fleming. Processing plate is a key core competency at Ryerson. Ryerson has over 100 plasma and oxy-fuel plate processing machines in the United States. Now, don't be afraid to raise your hand, hit the chat button for any questions. Okay, what max thickness can plasma bevel?
2 inches.
2 inches. Laser cutting. What assist gases are required to eliminate cleaning prior to powder coating? Same question for welding.
That would be nitrogen.
Okay. What is the benefit of fiber versus CO2 laser? And when should a water jet be used?
So CO2 technology is a few years older than fiber. There's a benefit in both. Older CO2 machines can cut thicker products a little bit better, but the new fiber technology is getting there. Fiber is faster. It doesn't shoot the laser beam off of a set of mirrors. It comes straight to the product. So that is a huge benefit. And then the last one would be water jet cut. Has little heat affected zone, almost virtually none due to the process. Water jet cut is great for stainless and aluminum and other type of alloys.
Thank you, Ray. All right, see how well you can remember your own presentation. What was the acronym for laser?
light amplification by simulation emission of radiation.
Excellent. Is laser more expensive than plasma?
Sometimes it can be, but not usually. You know, they're both very competitive. It depends on the thickness that you're processing.
Would laser cutting melt a ACM material as it is cutting?
If it's aluminum, it has a tendency to melt the material ahead of it due to the speed of the laser on certain thicknesses, but it's a pretty refined cut process. So there's really not a melting, it's just a cutting away.
Okay. How does plasma cutting affect the hardness of the material or metal?
Plasma is pretty fast. It runs really fast. It also, in many cases, runs on a water table, which keeps the metal fairly cool during the cutting process. The edge of the plasma is a little bit harder. You know, lasers can be the same way versus oxyacetylene runs a lot slower.
Okay, thank you, Ray. One more. How do you avoid heat warping in cutting a 400-inch long part on a plasma nest?
So that's a great question. I mean, the best thing is to bring the water up in the plasma when you're processing. The plasma machine is going to run really fast. That in itself will help eliminate warp, distortion, twist, bow, camber. So plasma is definitely the right option for that type of part.
Excellent. Well, Ray, you are now off the hot seat. Thanks to everybody on this webinar with all their activity on the questions. It's really appreciated. Makes for good discussion. Next up, sheet metal fabrications. Did you know Ryerson is the largest aluminum and stainless steel sheet distributor in North America? Professor Jones, the chalkboard is yours.
All right. Thanks for the introduction, Steve. Hey, everyone. My name is Jarrett Jones, and I am the sales manager at LaserFlex, a member of the Ryerson family of companies, located here in the upstate of South Carolina. As Steve mentioned, we are going to walk through an example of a component being produced from sheet material. This particular example is utilizing a 1/4 inch thick, high strength, low alloy material. For this exercise, let's assume our customer has communicated that their intended annual usage of the part will be right around 1,000 pieces per year. Our goal here is to determine the most viable processing method that meets all of the customer's requirements outlined on the drawing at the best possible price point. Please note, our example would ultimately require a forming process performed on a press brake, but for this exercise, we are mainly going to focus on the first stage cutting processes. In this example, we'll consider 3 manufacturing solutions. Those are plasma cut, laser cut, and hard tooling, which is also known as stamping. With a step-by-step review of the drawing, we will ultimately reach our goal of determining the best possible method for manufacturing this particular component. Our first step will be to review the title block in the lower right-hand corner of the drawing in order to gather some pertinent information. As we learned in Mr. Stelter's overview, the title block will list some tolerances that govern all features of the part. Let's review those. So as you can see, our drawing stipulates that dimensions in which there are 3 digits following a decimal point will require a tolerance of plus or minus 10 thousandths of 1 inch. With a quick review, we can see that there are 2 key features on this part that require this plus or minus 10 thousandths tolerance. Those are the 3.45 inch diameter hole, as well as the slot in the upper right-hand corner of the part. Just with knowing this, we can now eliminate plasma cutting as being a viable processing method, as even the most advanced high-definition plasmas are only capable of holding a cut tolerance of around plus or minus 30 thousandths of an inch, which is well outside the requirements for this particular part. We are now left with 2 options, which are hard tooling or stamping and laser cutting plus forming. Both of these processes can easily meet the required tolerances outlined on the drawing. So how do we choose which one achieves our goal of offering the most efficient production method at the most viable price? Well, let's consider the required annual quantity that we talked about earlier. We know that our customer will only need 1,000 of these per year. This piece of information will ultimately be the determining factor in choosing between the two options that we have left. For hard tooling or stamping, while it is likely the most cost-effective manufacturing method, once a component has reached full production, it carries a very high upfront cost for tooling. In order to stamp any unique component, custom tooling must be produced that matches that part design. This tooling can be tens of thousands of dollars or more, depending upon the end component's size, thickness, base material, and other factors. This custom tooling can also carry a very long lead time to produce, meaning it could take months before we are able to produce and ship the first usable parts to the customer. That upfront cost leaves us with a relatively simple equation. Will there be a large enough cost delta between manufacturing via soft tool methods, which are processes like laser cutting and forming on a press brake, versus stamping, to make up for and exceed the cost difference of the stamping tools? Given our annual required quantity, the answer on this example is no. There simply is not enough volume to justify the investment of the stamping tool. One other important factor to remember when considering a hard tool solution is that this option limits the customer's ability to modify the part. In the event there is a design change, the customer then needs to reinvest in new or modified tooling, thus bringing us to our solution, laser cutting. Processing this specific component on a laser allows us to offer the customer the most viable manufacturing method at the best possible price point that meets all of their requirements. It gives the customer design flexibility and allows us to manufacture and ship the initial parts in a matter of weeks. For some context, let's take a look at some of our lasers in action. The technology in that equipment amazes me every time I see it. Let's review some key takeaways. Our first step should always be to review and understand all aspects of a drawing in order to determine the most viable manufacturing method. We like to think of each drawing as an equation. Our customer is providing the equation and looking to us for a solution that meets all of their needs. Laser cutting can achieve tight tolerances and is cost effective. With the continuing advancements in laser and press brake technology, the cost gap between manufacturing using soft tools versus stamping is getting narrower and narrower, making the required quantity to justify a hard tooling investment higher and higher. Laser cutting, or really any soft tool manufacturing method, provides design flexibility to the customer and the end user. Component features can be changed in minutes, and most of the time at no additional cost, as we are simply updating CAD data. Thank you all for joining me in this exercise. I hope it was helpful in showing you how we go about selecting the most viable manufacturing method for every opportunity. With that, I'll be happy to take any questions you may have.
Great class, Professor Jones. Ryerson has over 30 laser cutting machines, including a new fully automated laser brake facility located in Portage, Indiana, beginning operation in April. Question answer time, hit the chat button and ask away. They're coming in feverishly. Placing a turret punch machine in the scenario from Jarrett would be more cost effective than a laser?
In some instances, yes. It really depends on the individual features in each specific part. So if you have some stamped features or extruded features in a part, then a turret can be very cost effective. I will say that there has been significant advancement in press brake tooling as well. So if you have a lower quantity, maybe less than 100 parts, sometimes it's actually more cost advantageous to run that via a soft tool solution, which would be laser and press brake. Believe it or not, there's some pretty impressive press brake tooling out there that can make up for a turret.
Could multiple sheet thicknesses, for example, 0.022 or 0.030 inch, be used on the same flat pattern of sheet metal parts? Would the difference alter the final product enough to justify two separate models?
So we can absolutely cut the same part or the same component out of two separate thicknesses. However, you can't do that simultaneously. You could really only cut one sheet or one sheet thickness at a time on a machine. But it's no issue to cut the same feature out of varying material thicknesses.
Will fiber lasers eventually 100% replace CO2 technology?
I don't think so. Over the long term, fiber lasers are significantly faster, but there are still useful areas, or there are areas where a fiber will run so fast that automation or human unload just simply can't keep up with it. So if you have a sheet and you're really only cutting two large parts out of it, it really doesn't matter how fast the laser is cutting it. What matters is how quickly you can get those parts out of the way so that you can cut the next ones. So with fibers being so much more expensive than a CO2 machine, you really can't justify the investment on certain items.
At what point would you normally switch from laser to plasma cutting?
So that's really going to be tolerance based and thickness based. So, we can cut up to about 1.25 inches thick on the lasers in carbon specifically. But once you get kind of tighter tolerance and plus or minus 40 thousandths of an inch, plus or minus 30 thousandths, then you want to go with something like a laser that can hold a tighter tolerance. It's not always a 1-to-1 with just material thickness.
All right, a question that I think I can answer is the availability of these offerings from Ryerson the same for people in Canada? Yes, Ryerson can offer services throughout North America and Canada as well. So yes, we do have not only raw material, but offer all fabrication services. Okay, Jared, you are now off the hot seat. Now that we are all laser focused, let's jump on the Ryerson bus to our next class. By the way, the Ryerson bus includes plate, sheet, and long products, but is powered by quality. Professor Driver, the wheel is yours.
All right, thanks, Steve. And my name is Tim Driver, and I manage a network of fabrication shops around the country, so we can just about make any part you need that's made out of metal. A lot of capability nationwide. But excellent quality is a requirement from our customers, and we expect quality in everything we buy from our customer, and our customers are no different than us. Our parts wind up in everything from golf carts and snowmobiles to large agricultural and earth moving equipment. So the parts must perform the required function in each application. Every step of the manufacturing process matters. and it starts with a mill. At the mill, they make plate, tube, sheet, and bar, and at the mill, those are created from the raw materials. The mill then checks the chemical composition and the strength and ductility of the metal. They certify to Ryerson that the metal conforms to the specification by providing a certificate of analysis or a certified material test report. And now that the material properties have been verified, we must assure that the part is made correctly. Now, this requires a programmer to create a program for the machine to properly cut, form, or machine the part like you saw in some of the other presentations. It is critical that the program is created, entered, and checked before it's used in production. So now out on the production floor, the machine operator performs additional quality checks. The operator reviews the processing instruction sheet and then confirms that the correct program is loaded for the part that is being produced. The first piece of the new part that comes off the machine is checked to assure that the part meets the drawing dimensions and tolerances required for the part to properly perform its intended function in the end product. And you saw those tolerances called out in the title block in the drawing that Matt talked about. And we have to check and make sure that that part meets those tolerances that are required for that on that drawing. But how do we check these critical dimensions? What tools are available and how are they used? Well, most people have seen and used a tape measure around the house or in the shop, which can tell you if the size is correct within about a 1/16 of an inch. Well, that's a good start, but many parts require closer measurements. A tool called a caliper can measure parts within 1/1000th of an inch. This is a useful tool for length, width, and diameter measurements. Now, if the part has a bevel, or if it's formed to a specific angle, the operator can use a digital protractor, which can measure an angle within 1/10 of a degree. But what if the part is large and has complicated shapes and curves that have to be measured? Well, the latest technologies in laser scanners are required to assure that the part matches the 3D model that we talked about earlier. You can see in this video that 2D laser scanners are used to verify flat parts quickly and accurately. And now we have 3D laser scanners that you'll see here that capture the complete surface of the part which the computer software can then compare the surface of the actual part to the perfect 3D part. The software produces a color map, which quickly shows if the part is intolerant. So once the parts are verified as acceptable, they move to shipping and packaging where the final quality checks occur. The parts are visually checked for appearance to be sure that they are ready to go to the assembly line at the customer. The parts are packaged, arranged, and counted per customer requirements and delivered on time, ready for production. So that's a quick, very high-level overview of quality. I hope this is informative, and certainly we are ready to answer any questions on quality. Back to you, Steve.
Thank you, Professor Driver. Now that was a quality presentation. Did you know that Ryerson is ISO 9001 certified? Opening the floor for our last Q&A session. Don't be shy. We want everybody to be ready for the final exam. What is the tolerance of a 3D laser scanner?
So our 3D laser scanners can, depending on the size of the part, can measure down to 1/10 of an inch, or 0.0001 inches.
Does Ryerson utilize PPAPs in their quality process?
Yes, we do. We have several people within the Ryerson system that are familiar with and can generate PPAPs level 1, 2, 3, or 4 PPAPs as required by the customer.
Can you take scanners like you showed on the video and discussed to a job site to map out specific parts and what might have been, on location?
Yes, we can. We have 4 of our new state-of-the-art 3D scanners in our system that are portable and can be transported. They come with shipping cases ready to go and can be transported on the airplane or by car as needed around the country.
Does Ryerson inspect the steel for defects before manufacturing?
Usually the inspection the steel is not checked for anything but visual defects, whether it's rust or exposed laminations or something like that. Usually the inspections are done after the part is produced. But if the customer requires internal examination, you could do an ultrasonic or radiographic examination before you cut the parts.
Do machine operators inspect the parts as they're produced on the shop floor?
Yes, they do. So the machine operators will take, as we mentioned, the first piece that comes off the machine and check all the critical dimensions. And then usually, depending on the volume of the job, we'll check every 10th, 15th, or 20th piece that comes off the machine to assure that the machine continues to operate properly.
2 more, Tim, and then you're done. What does Ryerson buy their plate with a flatness specification? If so, what?
So, yes, that's a very good question. We do buy plate that meets mill tolerances, which are from a flatness standpoint is rather loose, but we can order flattened material, and we also have material flatteners that we can use to bring the plate within whatever flatness we need. And now we're talking, you say maybe 30 thousandths over 36 inches, something like that. It depends, but we can get it as flat as we need it.
And finally, what traits would you look for in a partner to ensure the highest quality?
So when we go out and audit partners, we look for how robust their quality system is, and we will walk the process from front door to door to ensure that the information is carried over from the drawing to the programmers to the machine operators to the inspectors to the shippers on the top floor. And what's very important to us is that that our partners can do this repeatedly and accurately month after month.
Great job, Tim. Thank you very much. Well, I hope everyone had as much fun as I did going back to school today. To recap, Matt Stelzer educated us on Intro to Fabrication, the elements of a print, and its impact on choosing the right fabrication path. Zach Hicks walked us through the decision criteria, building a long product supply chain. Ray Fleming laid out the different options when processing plate products. Jared Jones talked sheet metal cutting and forming, and Tim Driver wrapped it up with how Ryerson manages the quality process through each step of a project. Where can you find us? Check us out at ryerson.com. Sign up for Cup of Joe, our monthly metal commodities podcast presented by Nick Webb, our Director of Risk Management and Commodity Hedging. You can review last year's Metal 101 on Ryerson's YouTube channel, as well as watch this presentation starting tomorrow. So congratulations to all the graduates of Metal 102. Now go forth with this knowledge and fabricate successful solutions for your organizations. Thank you and goodbye.